Okay, so let's see how QR factorization is done in linear algebra. So the idea of QR factorization is to take a matrix, let's call it A, any matrix, it doesn't have to be square, it doesn't have to be invertible, any matrix A, and to factorize it into two matrices. One is called Q, which is an orthogonal matrix, and the other one is a upper triangular matrix, which is called R. Now, the properties, remember, of an orthogonal matrix is this: Q transpose Q equals I, and Q transpose is the inverse of the matrix. This is by definition for orthogonal matrices. Now, A can be any matrix, doesn't have to be square as we said, so it can be M on N. And we get Q, which is M on N, and R, which is the upper triangular matrix, which is N on N. This is the factorization. Now, what it is used for, you can see here the applications. We can use it, for example, to solve in least square problems. We take ax will be ax equals b, and you can factorize a into qr and just take q to the other side of the equation by remembering that the inverse is just q transpose. So it helps you solve those equations. And you have other applications. Now, the question is how we do that. So let's start with examples. This is example, you can see A here, which is 1, 1, 1, 0, and you can factorize it. We will see in a minute how we do that. You factorize it into this orthogonal matrix. You can see that the columns are orthonormal to each other. And an upper triangular matrix. This is the Q, and this is the R. And so this is a QR factorization. Now, how did we do that? Now, again, let's take this matrix A, 1, 1, 1, 0. Let's take the first column. This will be the first column of our Q matrix after we will normalize it, because we need orthonormal columns. So we take the first column from A, which is this one, A1, and we normalize it using its norm. So dividing A1 by its norm, giving us this one, because the norm is square root of 2. So this is the normalized first column, and we call it Q1. This will be the first column of our matrix Q. Now we get to the second column of A, this is 1, 0. We need that this column will be orthonormal to what we just found, to Q1. But it is not, so we need to take the part that is not orthonormal, remove it, and normalize the vector. So that's what we'll do. So A2 will be 1, 0, and we will take the projection of A2 to Q1, and we want to remove this. This is the projection, so let's remove it. The projection just multiplied by Q1, so it will be in the direction, and we will remove it. We take A2, subtract the projection, and we are staying with U2, which is the vector from A2, which is orthogonal to Q1. Now it's orthogonal, but we want orthonormal, so we need to normalize it. So you get a normalized vector. So let's divide by the norm of U2. This is the norm. So we take this and divide by U2. You can see that Q2 is U2 divided by the norm of U2, which is this calculation. We get 1 divided by square root and minus 1 divided by square root of 2. So we get this Q2 here. So we have Q1 and Q2. Those two are normalized vector, which are orthogonal to each other. So they will be the columns of the matrix Q, which will create an orthogonal matrix with orthonormal vectors as columns as needed. Now, for the upper triangular matrix R, what we are doing is taking the norm of A1, which is here, the norm of U2, which is here, and A2 in a product with Q1, which is right over here. This creates an upper triangular matrix. This will be our R. And here it is. Take Q1, Q2. Here they are as columns of the Q matrix, of the orthogonal matrix. And this calculation will give you the R matrix, which is right over here. When you multiply, you'll get A. Of course, this is the factorization we just calculated. So here A, we factorize it into Q, orthogonal, and R, upper triangular matrix. And that's it. You can see it with a very nice Oh, I thought the denomination. Anyway, this is it. This is the QR factorization for a matrix, and you saw the applications. And I wish it was useful and helpful. Thank you very much. And that's it for now.